Hey everyone, back to our ball example here, falling into the cloth and potentially breaking our weld constraint here. And this time the settings are in a way that it doesn't break. And what we want to talk about in this video is a very important concept, and that is mass. For the first time we actually want to use it because we heard of mass before, and that is in the context of forces. And all we learned there is that almost all forces ignore mass. In theory, the concept is the higher the mass of an object, the less a force would actually apply to it. And this is why it's turned off, because that's kind of the opposite of what people would expect. So we can ignore this, but it's nice to know. But mass plays another very important role, and that is whenever objects interact with each other. And this is something we have right here. And this will also play a role, very important later on, for example, in RBDs or destruction simulations. So in Vellum, we learn about this concept the first time, but it's something that we will see again later on. So the first thing you have to understand is that actually there is already mass set on all those objects. If you look, for example, what comes out of the cloth constraint for our patch here, for our cloth, you can look for the attributes and you will actually find that there is already a mass attribute that is automatically calculated for the cloth. Of course, the same is true for our sphere here. There's a mass attribute calculated with, all kinds of numbers. So where is this coming from? This is actually coming from the constraint itself in the very beginning, and we haven't talked about this yet, but there is a mass attribute and a thickness attribute. The thickness attribute we will talk about in the next video. For now, we concentrate on the mass. To understand this, let's first change this, because we can set the mass in different ways. Let's start with unchanged, and let's do the same for the sphere, both to unchanged, and let's see what happened. We actually set the mass to -1. What the hell does -1 mean? It just means basically there is no mass, or the mass is infinitely small, or no mass at all. It's, it's deactivated basically. And what you can see, if we turn this off by setting it to unchanged for the sphere and the cloth, and we press start when we look through the Vellum solver, you can see it's basically like before. Well, a little bit has changed, fair enough, but fundamentally not much has changed, at least not between them. So let's turn this back where it was for the cloth, and this was actually calculate varying. We'll talk about this in a second. And for the sphere, let's now change this first to set uniform, which is the second option. And this is a way of setting the mass, as you can see, directly. So let's say when we look into what comes out of the cloth, you can see the points have a very low mass number. So let's make sure we have a number that is much higher than that for the sphere by setting the set uniform. And again, be careful that you only change this on the constraint for the sphere, otherwise it doesn't make sense. And we want to give that sphere, each point of it actually, a mass of 100. And let's see what happens. And when we press play, you can see that our sphere now just breaks through the cloth as if there was nothing. So let's run this again. It seems like it's not even stopping from it. Why? Because the mass of the sphere is now so much bigger than the mass of the cloth that the energy distribution between the one is clearly on the side of the sphere. So the sphere kind of wins. And this is a very important concept for everything in Houdini, really. And this is the first time where we see that. Now, you might have noticed when we run this actually that the sphere is deforming quite a bit. This has to do with the forces here in the Vellum solver. Under forces, there's a wind drag, so basically like an air resistance. There are two ways of turning this off for now. Either setting the wind drag to 0, or you just turn the wind force off, and then this is gone for now. And that makes it a bit easier to judge what's going on. Now, let's lower this to 1 and see how it behaves then. And it's still, as you can see, very strong. So let's go further down, maybe 0, 1. And it still breaks through. So interesting enough, we seem to have to lower the number quite a bit, because remember, the numbers of the cloth were pretty low. And we will talk about this in a second, why that is. But as you can see, if you put it low enough, then the mass of the sphere is not that much stronger than the mass of the cloth anymore. And it will not, so to say, win the impact. So as you can see, this is a cool way of controlling your, interaction with objects in a simulation without having to change the constraint settings. You just change the mass of the objects that are in the simulation. But the thing is, we currently set it with set uniform to an absolute number. So if we quickly filter for mass, you can see that the number we just set is directly set to each point. But that's not the default. The default is calculate varying, which is actually the same as calculate uniform. The difference is only that we can't scale it by attribute, which we'll not talk about here because you already kind of understand the concept. But what is important here is that in both cases, it uses a density number. And that means that it calculates the mass based on the volume of the sphere. Keep that in mind. This will play a role later on in RBDs again. And as you can see, the mass is now calculated automatically based actually on the size of our sphere. So if I increase the size of the sphere to something really big, unfortunately, it's not that easy to show. So let's just select a couple of points, maybe those, and only show the attributes for them. And let's lower it to a really small size again and look at the numbers. And it's 0.0002 in the mass. And if we bring it back to the big scale, it's 0.06, so something like 30 times bigger. So as you can see, the size of the sphere influences the mass it will have, which of course is very natural in reality. The bigger something is, the higher the mass, but maybe that's something you don't want. So you can choose if you want to set an absolute number or a number that will take the volume into account. Either way, what you can do is if, like now, for example, our sphere is not strong enough and we want it to break through, and you can see it broke it a little bit, but just not quite, then instead of lowering the breaking threshold, we can just go into the constraint again, and let's say we, multiply the density by 3, and whatever the size of the sphere is, the mass will now be 3 times as high. And if you run this now, you can see it actually does break through. So this is what we use it for. We control our simulation with it. We will talk about this again, as we heard multiple times now, in the RBD section a bit more because it plays a big role there. But just keep that in mind. You can either change the density, which you usually do, then it's based on the volume. So increasing the sphere will also increase the mass. If you don't want that, you can just set it to uniform and put in an absolute number. Just play around what works in your case to control basically the energy distribution. A small warning here, by the way, if for some reason you end up with a mass of 0 somewhere, then your points will be deactivated. This can happen when you have a varying or uniform, so automatically calculated mass. For some reason, sometimes if you have a weird geometry, you can end up with a mass of 0 and then the point will be deactivated. I don't have the case like this here, so let's quickly just play around to see the effect. If I would select a couple of points, I don't know, some on my sphere and some on my geometry, it doesn't really matter. And then for those, I set the mass to 0, which of course I do after the Vellum cloth where it is calculated and generated. Then you will see if I run this, that these points are basically deactivated and don't move at all. So if in your simulation some points deactivate for no reason and you don't know where that comes from, check if maybe their mass is 0 and then just overwrite the mass with some number maybe that you just look up for the other points, and then the points will move again. In the next video, we will talk about another important property, which is the thickness. But for now, as you can see, you can change the density, which results in a different mass, to control the energy distribution when two objects interact with each other. So for now, I hope this was helpful. Thanks very much and see you later. Cheers.